Well, hello, this is Miss Dagenford, and we're going to be looking at polarity and non-polarity of molecules. And this is going to be really important to understand because we will be looking at the chemistry of biological molecules throughout the entire year. So our objectives are going to be to describe the behavior of a polar bond and also nonpolar bonds, and then to explain how this polarity and nonpolarity cause interactions in a biological system. So first, let's just go over some definitions. When we think of polar, you might think of the North Pole or South Pole, or the magnetic poles in a magnet, or maybe even the polarity between two groups. The political parties, they're poles apart. So you can see that in the definition already, we have this idea of a separation, that they are far apart. And so polarity is a molecule or a part of a molecule, we're going to get to that in a little bit, a part of a molecule where the atoms share electrons unequally. And this ends up resulting in a dipole where those two atoms, or a small group of atoms, one part ends up having a partial negative and a partial positive charge. Now, it's not going to be a full charge, because if that were the case, then we would be looking at an ionic bond. They're still sharing, they're just sharing things unequally. Now, what leads to having a polar molecule? Well, they're electrically asymmetrical. Now, this ends up coming back to a term that you probably remember, electronegative. An electronegativity or electronegative is referring to how much pull an atom has for electrons. So the higher the electronegativity, the greater the pull for electrons. Sometimes, and this is a bit anthropomorphic, but sometimes you hear people describing them as greedy or an electron hog, and of course there's no emotions to them, but it's a useful idea. They pull electrons towards them. And you probably saw this chart in your chemistry class, but the electronegativity increases as we go from the left to the right. And one thing you'll notice is these groups of atoms up here, carbon, nitrogen, oxygen, fluorine, chlorine would be up there, sulfur, they're going to have some of the highest electronegativities. And then if you look over here, hydrogen's rather low, sodium, magnesium. So these are quite willing to give, or they have a low electronegativity. The electrons are pulled away, and then these atoms over here, they pull towards them, the electrons, and so the electrons are attracted to them. Part of this has to do with the fact that, well, you have more protons. When we get towards the right here, you have more protons, and more protons are going to attract more electrons. And so oftentimes you will see an atom that has a high electronegativity. If it's paired with one that has a lower electronegativity, that's what's going to create this unequalness. And so the other factor is polar molecules are geometrically asymmetrical. And so water is a classic example of this. Because of these two unshared pair of electrons, water has a bent shape, and that contributes to that polarity. So the partial negative charge is going to be on that side with oxygen. Oxygen tends to have that partial negative. And then hydrogen is going to have the partial positive. Now, I know this is just a silly diagram, but one thing that helps me just kind of remember this, and if you've had me before, you've seen me draw this And it is ridiculously silly, but I still like to use it. And so imagine you have oxygen as this big strong man, and he is in a tug of war with our little featherweights over here, and that would be hydrogen. And I'm showing him being angry, but really it's just the fact that he's stronger. So he's going to be pulling the electrons closer to him. And if that's true, then that means he's going to have the more of the negative charges, and that's what creates the dipole moment. And so overwhelmingly, we have oxygen. Here's another diagram. Oxygen with more negative charges towards its side. And then hydrogen doesn't have the negative charges, and they have the proton. So hydrogen generates a positive charge, a partial positive charge. So here's just some examples. Here we have hydrogen and fluoride, and then what they show with the arrow is pointing where the electrons are being pulled towards. So fluorine's going to have a higher electronegativity. Here's oxygen. Oxygen is getting the electrons pulled towards it. And then notice this one, even though chlorine has a higher electronegativity, it's very geometrically symmetrical. There's an equal pull. So because of this, there's no one part of that molecule that has the electrons than another part. If sometimes I like to draw it with a different color pen. Imagine my red pen is where the electrons tend to be. Well, fluorine would have more of the electrons. Oxygen would have more of the electrons here. But because there's an equal pull, there's no one place where I would shade with my red more than another place. And so that spreads the charges apart. So this is nonpolar. What that means is this has no partial charges. It tends to be very neutral. There's no one spot that has any concentration of electrons or protons, whereas you would say this is a partial negative, this is a partial negative, here would be a partial positive, here would be a partial positive. Now this creates some very interesting interactions. Here's some more examples. Just the way they've drawn them is very nice as a three-dimensional. Polar molecules are attracted to other polar molecules because of those charges they have. And because they are attracted, they're going to create hydrogen bonds. Now, hydrogen bonds, the bonds is a bit of a misnomer. It really is an attraction. So it's not like a covalent bond or an ionic bond. It's between two molecules. Attraction between two molecules. And the attraction comes from the partial positive of one molecule and the partial negative of the other molecule. So here we have water, classic example where here we can label, here's our positive, partial positives, partial positive, partial positives, and then here we'd have our partial negative, negative, and you can see there's an attraction between the partial positive and the partial negative. Here would be another one. Here is the attraction between a positive, and then here's the negative. There's the attraction between them. And that would explain why on the hood of your car, after it rains, if it's nice and waxed, the water beads up. And that's because all of the water molecules are pulling together. They're attracted to each other. And this produces another property called cohesion, where the water molecules are attracted so greatly to each other that they pull together. This creates the surface tension on the surface of water, where you see the little water striders. They can skate on the surface of the water. Their legs don't break through it. So polar molecules can have these hydrogen bonds between them. Now, non-polar bonds, because they are neutral, you will not see those partial positive and partial negatives. They're electrically neutral. That's going to be very, very important. Now, organic molecules for this class, what you're going to notice most is the OH, the oxygen bonded to a hydrogen. And so, for instance, here, this is going to behave very similar to water. The oxygen is going to have a partial negative. The hydrogen is going to have a partial positive. Forgot to mention this little squiggle, that's a delta, and that's how we designate partial. So all of these oxygen molecules are going to have a partial negative. All of these hydrogens are going to be partial positive. Now, what about these hydrogens? Well, notice they're connected to a carbon, so we don't have that same dipole. So we're really going to be looking at, let me highlight these. We're going to be looking at a difference of these oxygens that are then attached to the hydrogens. That's where we're going to see the polarity. Now, if you color it, you can really easily now see, if I drew a water molecule right next to it, now we can start to see that the attraction, because water would be attracted very nicely to the glucose molecule. So here would be a hydrogen bond. Here would be a hydrogen bond connecting them together. So if you had a huge amount of water surrounding this glucose, water's going to love it. It's going to be attracted to it. And glucose is a sugar. And think about what you know about water, glucose, sugars in water. They dissolve very nicely. Over here, this is electrically neutral on the right. This is a non-polar. If we were to try to draw the parts of the electrons, we would not see any area where that has a concentration of the electrons. It's neutral. So water will not be attracted to it. So here's our partial charges. There's nothing for the water to be attracted to. It's just going to bounce right off. So here would be an example of a nonpolar. Now this is very similar to an oil. So we know oil and water don't mix. So here's an example. This is a really nice picture of water surrounding glucose. So notice the water molecules are all being attracted to the individual glucose molecules. Now they're not going to be able to pull the glucose apart. Like it's still going to stay glucose, but they can pull the glucose away from other glucose, and that's why sugar dissolves in your coffee or tea. And so polar molecules are not attracted to a nonpolar molecule, but notice, be careful that they're not repelled. In this picture, what happens is the water molecules, they just are attracted so much to each other that they just push away the nonpolar section of this molecule, but that doesn't mean they're repelling it. They're just not attracted to it. And one thing that we're going to notice is that molecules can have polar and nonpolar sections. So for instance, this end over here, this is going to mix with water very nicely. The nonpolar end will not. So for instance, that would be the part of an oil molecule. These are going to be really important, these interactions. So for instance, if we had a molecule like this, and I hope that you can start to see if we had a molecule like this, hopefully you could see how water would be attracted. What parts would water be attracted to? And then we'll talk a little bit more about this tomorrow. So thank you so much.